The last one we look at is what is called as paired t-test. Before we go on to variances, the last one in terms of mean is paired t-test. Any idea what is paired t-test? What do we mean by pairing? Okay, so you assume that this x1 y, so x and y, if you take two random variables, in this case x1 and x2. Okay, so let us take with an example, then it is better to understand F distribution with an example. Let me see if they have an example. So this is the paired t-test is a special case. Okay, so let us look at this examples. Okay, each pair of observations, say x1j and x2j is taken under homogeneous conditions. So let us say an example, suppose that we are tested in comparing two types of tips for hardness testing machine. You have a machine, you want to test your tip, okay, you want to test your tip for measuring hardness of a sample. Okay, so we are interested in comparing two types of tips for a hardness testing machine. Okay, the simple case in our analogy would be to actually have two kinds of, you have seen this, have you seen this glucometers? There are multiple kinds of what I say, the needles, right. The needles are not even uniform, the needles are, there are standard needles, but there are many of them, it is not always one needle fits, there are many needles, some of them have higher pain, some of them have lower, etc. I do not know whether you have tried, okay, each one of them, even in syringes, injections and needles, there are so many companies that make needles, and even among companies the cost varies, which is one of them. Do you know of any needle making company? No, syringes, needles, not even aware, huh? Dispovan, okay, that is the easiest, because you see in that thing. BD, have you heard of a company called BD? It is one of the biggest marketplace, Becton and Dickinson, one of the biggest market players in manufacturing needles and syringes. BD also does, and there are many other companies who do needles. Needle is not a rocket science to do, right, I mean, even rocket science is not really difficult today. So needles many companies do, right. So now you want to compare which one do you want to buy, each one of them, and all of them are not same cost, then there is no point making manufacturing, each one of them has its own pros and cons. Okay, so now we want to compare these kind of needles, let us say. Okay, so there is a machine, in this case it is a hardness testing machine, presses the tip into a metal specimen with a known force. Suppose I give a known force to each needle. Okay, how much depth of depression caused by the tip? Okay, so how much impression does it leaves caused by the tip? The hardness of the specimen can be, by measuring the depth of the depression caused, the hardness can be determined. In this case you have a machine, you want to measure that, use that, you want to compare the tip of the machines, and the idea is if you fit a tip to the machine gives a known force and it creates impression, the depth, and knowing the depth you can measure the hardness of the specimen. If several specimens were selected at random, if several specimens of the random, half tested with tip 1 and half tested with tip 2, okay, and a pooled or independent section was applied, the results of the test could be erroneous. So what am I saying? If you do it with 2, so if I do hardness, let us say I do 2 tips, I have 100 metal pieces, I am testing the hardness of the 100 metal pieces with 50 with one, 50 with other, and I start doing hypothesis testing, okay, on the hardness, they say you will get a wrong answer. Why? Each of the tip itself is different. So when you want to compare the hardness, correctly measure the hardness of a specimen and compare, what you should do? I should pair the tip with the specimen. You understand? I have 100 metal pieces, I want to test the hardness of 100 metal pieces. It is like saying for 50 I will use one sensor and for another 50 I will use another sensor. Does it make sense? No, right? You have to pair the sensor with the. So if I want to exactly know whether what is the whether what is the hardness of this material piece, what should I do? I should have used both the specimens, both the sensors on the same device, only then I should be able to say, then I can say the difference, the hardness is difference is not due to the sensors but truly due to the metal piece. You see a point here. So suppose I use 50 metal pieces one sensor, 50 metal pieces another sensor, the readings I get will be have bias because of variation in sensor itself. You will have a variation because of the sensor used to measure the hardness itself. You understand the point? It is called basically confounding effect. You will not know the variation in the metal effect, the hardness is due to the sensor you used or is it truly due to the material used, right. So that effect is the confounding effect, and that is why you will get erroneous results, because confounding effect will be there. You randomly do 50 with one sensor, randomly do another 50 with one sensor, you cannot come to any conclusion about the hardness, because that is where, so that is where you want to pair them, okay. So the metal specimens could have been cut from bar stock, different heats, different conditions, okay. Observed difference between mean hardness readings for the two type of tips can also include hardware differences between specimens. So what do we do here, okay. So what do we do here is, we want to analyze the difference between hardness readings on each specimen. So I have a specimen, I am using sensor 1, tip 1, and I have a tip 2, I am using that. So I am going to pair them, okay. So what kind of pairing you are thinking, what kind of pair we do? We have pair the tip with the metal piece, okay. So this, let x11 x21 be a paired observation, where we assume that mean and variance of population represented by x1 mu1 and x2 mu2. So in this case, this what will be x1 in this case, x11 in this case, x21 in this case, in this example, tip 1 specimen 1, tip 2 specimen 1. Now I have the hardness reading taken from two different sensors, okay. That is, specimen 1 is going through both the tips, that is what this x11 x21 is. X11 is tip 1 specimen 1, x21 is tip 2 specimen 1. For each specimen I am going to pair. Now what can I compare? I can say I can compute the difference between these two, I can compute. So I have these pairs, now I have these pairs. So what is deviation? The deviation is nothing but x1j minus x2j. This is the deviation in hardness due to using tip 1 versus tip 2, okay. So let us think of this example. In fact, even hardness is a simple case. So suppose I want, you all know calibration, biomedical instrumentation, we want to do calibration, right. Suppose how do I calibrate my let us say a weighing machine, how do I calibrate? I have a weighing machine, I want to calibrate, how do I do? By putting known weights on instrument, or sometimes we do what is called as a calibration using the, you have primary calibration, secondary calibration. Have you heard of this? Primary calibration is where it is again done against the standards, known standards. Known standards is what? What is the known standard of kg? Earlier it used to be platinum iridium cylinder. Have you heard of that? Platinum iridium cylinder, and then for length they have a standard, and then for time also there is a standard. All standards they have it in, I think, France or somewhere, the standards are preserved. And then there are equipments that are calibrated against this primary standards, then there are equipments they are calibrated against secondary standards, etc. All of them cannot calibrate it against primary standards, right. So then there is primary, secondary, tertiary calibration happening. Now suppose I want to calibrate my, I say my okay, what is the sense, your accelerometer. I have one accelerometer in this phone, another accelerometer here. I want to make sure this is my, let us say, the ground truth accelerator, or the one which I want to calibrate against or which I want to refer against, and the mobile accelerometer is one test. So ideally both of them should be, the difference should be between should be what? 0. Now if I use this sensor in some 10 locations and use this in some other 10 places, can I even compare? No. What should I do? I should use both the sensors on same piece. That is the same thing we are doing. Now what is my interest? I am going to say this sensor is as good as my reference gyro, reference accelerometer, right, or the deviation between these two is statistically 0. It will not be exact 0. What am I going to claim? This accelerometer reading is as good as the reference accelerometer reading, and the difference is statistically 0. You understand what context we are talking? This comes in calibration all the time when you want to compare. This is the best one, and my method or my sensor is as good as the what is existing, the ground. Okay, you may have developed because you wanted a lower cost. You might have developed a product because it might be of lower cost, lower accessibility, less whatever reasons, but you always want to compare against the ground reality. So if I compare these both, then it should be tested on the same species, same specimens or same samples. It cannot be tested on different things. Okay, suppose you develop a drug and you have another drug. You take a drug, it worked on 50 people. Okay, you gave it to 50, let us say 50 people, and the ground truth, the already existing drug, you gave it to another 50. Now can you compare their efficacies? Because these 50 people are different with different background conditions. The ground truth, whatever the best medicine you gave or whatever existing you gave it to different 50 people, how can you even compare? There is a confounding, because the efficacy of the drug could be just because these people are more drug absorbing or whatever reasons, they do not have prior conditions, etc., whereas the other 50 people, whomsoever you gave these are ways in which you can actually lie. Basically you have to be very careful in doing experiments, otherwise you will invariably end up saying something which is not true. You see the problem in drug delivery or even in any biomedical, when you want to compare against what is existing, you have to take care of all of this as much as possible, because if the sample size samples you select plays a very important role. If you cannot test on the same sample, then your result is actually confounded. You should at least, and the inherent problem is biomedical is, if you develop a drug, can I develop 2 drugs to the same person? You develop a drug for, let us say, a fever, and you want to compare its efficiency against Dolo 650, and you have developed a, let us say, cost effective or whatever, or that your mg level is lower, so that the side effects are lower. But how do you compare? Suppose you give Dolo 650 to the person, you cannot immediately give your medicine to the drug. It is like, double whammy, he is taking 2 tablets for fever, right. These are the issues. Then you have to have test cases similar. You cannot test on the same person, how similar they are. So these are the questions to keep in mind. You take a 80-year-old and then give you a Dolo 650, and then for a 20-year-old you give your medicine. Naturally your medicine will work better. because the 20-year fellow would have recovered even if they may not have given the drug, whereas the 80-year-old will definitely need drug for a longer time. You cannot compare efficiencies, right. So, yeah. X1 and X2 will be independent, right. Why will, where is question of independency, because I am not testing on the same sample. X1 and X2 will be independent. What is X1? The effect of drug 1, and X2 is the effect of drug 2 to reduce the symptom.
Where we are testing the drug 2, that depends on where we test for drug 1.
I cannot, the problem with biomedical in this case is I cannot use the same sample itself. Drug 1 on sample 1 and drug 2 on same sample 1 is not possible, because you cannot force a person to take 2 drugs for the same issue, first problem. Then even if they take, there may be interactions of the 2 drugs, okay. So, you have to create drug, you give drug 1 to sample 1, but drug 2 to sample 2, the sample 2 should closely resemble sample 1. Only then I can do this kind of hypothesis testing.
Is there not a dependence between
drugs? Why? Where is the dependence?
Like for the accelerometer example, so wherever then we are using X2.
See, I am using both the accelerometers, and I can put both the accelerometers on a motor, and this gives the ground truth. I know this is the best. This reading should be as close to the ground truth, that is all. I put it on motor 1, motor 2, motor 3, motor 4, take some 100 readings, do the hypothesis testing on difference, and I am going to say statistically these two have no difference, right. What will be the problem with unpaired t test, that is no pairing, is if I put on 50 machines and if I put on different 50 machines, the machines itself will contribute to effect, and that is why both the sensors should be located for the same unit, so that you can compare the sensor readings or compare the drug readings. In case of drugs it becomes even more complicated. Ideally I want to do like this, but in case of biomedical, especially when it is something taken inside drugs, that is a problem. If it is suppose an EEG machine, look at today many of them come up with their own ECG machines, right. How do you benchmark your ECG? How do you want to benchmark your ECG? That is the easiest question to ask. You build an ECG device. ECG device is building is not difficulty today, right. 12 electrode, you can make your own amplifiers by borrowing chips in from AD etc. Get chips off the shelf, you can assemble and you can build a ECG. If you notice Suresh Devasagayam, if you are aware, he has built his own ECG in CMC Vellore, and there are some other companies have built ECG at much higher frequency, okay, acquisition at much higher frequency. So now how do I compare ECG? Now how do I know that my ECG is good? My ECG device, how do I say that it is good? If you build one, how are you going to compare? You build a device, how are you saying that it is going to be good? It is better, it is working the way it should be. You have already standard electrode ECG devices, standard ECG devices from market. Take the best one, there are so many. Collect ECG at the same time using yours and their equipment. Do the same test, do this test. You do it for 20 participants or 50 participants, do this, then you can statistically say that my sensor, whatever I have developed, is the same working as good as the what is in the market. That is all, right. That is the easiest way to think about it. So this helps us benchmark our, this kind of hypothesis testing helps benchmark our developed new products against the existing products, existing biotech product, biomedical sensors, instrumented devices, whatever. So you developed ECG or you develop an EEG or you develop EMG, all of this, or a PPG. PPG can be measured in 1000 ways. So suppose I develop a sensor to measure force, what do I do against? I have to compare against what is in the market. So use that on the same sample, take readings, compare whether they are statistically same or not. That is what this is. So here we are going to talk about difference between the reading produced by sensor 1 and sensor 2 on the same sample, okay. So this is what is pairing. So I have paired meaning the result produced by sensor 1 and result produced by sensor 2 on a single sample is paired together. So this is a pair. Like this you can have n pairs, okay, and I define what is called as a deviation, which is x1j, the difference between sensor 1 reading and sensor 2 reading on a particular sample, that is what is deviation. Now this deviation should be ideally 0 if you want both the sensors to be working the same way, the deviation should be 0, that will be my null hypothesis, or that could be my alternate, whatever case. In this case my null hypothesis deviation is 0, okay. So then you compute mean of deviations. The mean of deviations is what? Mu 1 minus mu 2. Then you could say the mean of deviations is very small number, delta naught could be 0 and your null alternate could be delta naught is not equal to 0. And what will be my test statistic? Same, d bar, d is mu difference is what? D bar is here mu x bar minus, the d bar itself is nothing but x1 bar minus x2 bar, right? D bar itself is deviation only. So you are calculating the mean of the deviations. So mu d is nothing but d bar plus or minus z alpha by 2 into sigma over root n. If your population is less, your sample is less, then it becomes T alpha by 2 with n minus 1 degrees of freedom. You understand? It is a usual normal distribution if population size is large, n is large, but remember n is paired here. So suppose if I say n is 20, then you should have conducted, you should have had 40 readings, because each specimen you collect 2 readings. So basically you have 40 samples if n is 20. If n is 30, you already have 60 samples because you are pairing it, okay. So this is paired t-test. This is very important when you are comparing equipments, the performance of equipments against some ground truth. So especially when you develop a new product, new biomedical device, be it assistive device, medical device, any device, the natural thing is to check against the ground truth or the best ones available. It should either perform better or equal, and equal to same, and your hypothesis could be it is even better, okay. So but that is the idea, clear? It depends on the underlying process. If the underlying process is dynamic, it has to be 1 to 1. If the underlying process is dynamic, it has to be 1 to 1. That is why when you do an ECG, both of them has to be started and stopped at the same time. You cannot have both of them were running different, because my heart rate is dynamic. So if we measure ECG for before, what are you comparing against? It is apple to apple comparison. So if the underlying process is dynamic, it has to be at the same time, okay. So remember, we did experiments where we were collecting heart rate, okay, when during an exercise, okay, some of you here during an exercise, okay, we could not collect during an exercise because they cannot wear a ECG monitor. I did actually calculate ECG using images. I mean I was calculating heart rate using just images, non-intrusive way, it is called RPPG, but I do not know how accurate it is. This is a classic example. I do not know how accurate my heart rate using remote photoplethysmography, they call it as remote photoplethysmography. Just from an image one can calculate heart rate, it is known, one can do heart rate calculation just by using images, okay. Now I want to know how accurate it is. What will you do? The time at which you calculate heart rate using your images, using a video, at that time they should be wearing a chest or whatever, for typically the chest one is the accurate one for calculating heart rate, and you can also take data from your watch at the same time. Then same sample you have 3 different readings, then you compare statistically, is my reading same as that of the gold standard chest, or at least is it same as that of the watch. Then you can say that my method is accurate. Now I have to do this with some n samples. Let us say if I do it with 100 people, I did it with 20, 30, okay. I did not get Gaussianity, but 20, 30, okay. But if I do with 100 or 200 people, then I can comfortably say that this is what. If you use Apple Watch for calculating heart rate, this is what they did. Apple has done with more than 60,000 people, I guess. I do not remember the number, 60,000 or 6,000 people, they have did this test, and they say their heart rate accuracy is as close as that of the ground truth worn in chest. So now you can comfortably wear it, and then the heart rate is as accurate as your chest. At least studies have done, statistical studies are conducted. How do they do it? This is a statistical test, paired t-test. Make sense? Clear? So the next class we will talk about variance, and we will start moving on to multiple random variables. Clear folks? So let us next class catch up with variance testing and then multivariate random variable, multiple random variables. Thank you.